Okay. Okay, so so you've got here this, you've got the average age. Now, this is possibly not enough to understand the age distribution, right? You see this E of theta that we've got here, E of theta, the age distribution. This is a lot of information. There's a large amount of information here. And we know that by the end of the day, we like to deal with just a few numbers and magically estimate the reaction rate and be able to design a whole reactor. And we'd like to continue this tradition of finding simple, quick ways of doing things. So we have one nice number now. We've said that we can estimate the average age in the reactor, but we are concerned that this might not be enough, right? You can imagine a situation like this. So let's say we have an age distribution that looks like this. And then let's say we have another age distribution, which looks like this. And you can see they have approximately the same average age. So their average theta is sitting around here. But you can see they have a very different distribution. So possibly there's a second number we should look at. And the way I've drawn this one in particular is implying that we need some measure of the width of this distribution. So that's where you can consider the standard deviation. So a standard deviation type of approach might work there. So we can think of writing something like this. So we can say sigma squared is equal to int not to infinity. Right, so we can't integrate to negative ages. Obviously, 0 is the smallest possible age, and then we do the same as before, E of theta, and this time this is going to be theta squared integrated in theta. Right, and if you are familiar with the concept of variance and standard deviation, then you'll be able to, well, in fact, it's not theta by itself, it's theta minus theta mean, theta minus theta. Right, so you can see here the current theta minus the average theta, that's and then times E of theta d theta. So we can think of E of theta d theta as the fraction of fluid elements of age theta. So the fractional amount of fluid elements having age theta minus the average age of all those theta, minus the average age, is an indication of how far on average our curve is from theta average. So that's basically the width of the distribution. So with that second number, we have a much better handle on the age distribution. There are other numbers. So for distributions, you also have what's called the skewness. So the skewness tells us, is the curve skewed on one side? So if your mean is sitting here and your curve is skewed to the left or right, then if it's to the left, the skewness will be negative. If it's to the right, it's positive. So the skewness, and then there's also the so-called kurtosis. So how far above the normal distribution is it? So skewness and kurtosis are two other numbers. But in this course, the mean age and the variance, those are the two defined. And in fact, we don't really use the variance that much anyway. So the mean we'll see many times. And maybe if I can ask you, what quantity would this be related to? What variable have you met so far that should be related to this theta over bar? Any takers there? So think about it. This is, if you like, the average age, right? Again, E of theta delta theta. that's basically the fraction of fluid elements in the age range, theta to theta plus delta theta. And that times theta, that's telling you how much a theta is contributing to the average theta. So you add all those together, that gives you the average theta in the reactor. In other words, that's the average age. So if you are looking at all the fluid elements in the reactor, that's the average age, right? And let's see. Okay, so network problems. So there's an average age that exists in the reactor, right? And what quantity does that relate to? Think about some of the quantities that we talked about before, right? Think about how does average age relate to the flow rates through the reactor? Right? If your flow rate went up, what would happen to the age in the reactor? Would it go up or down? So maybe in the chat, type a 1 if it would go up and type a 2 if it would go down. Well, that's counterintuitive. Make it a -1 if it goes down and a +1 if it goes up. Right? So if your flow rate goes up, what happens to the average age? So 1 says up, 2 say down. So if your flow rate goes up, let's think about what happens here. If your flow rate goes up, then that means you are moving faster through this reactor, right? So if you are moving faster through a space, you are spending less time there. So think about running on a track or running across something, right? If you walk across it slowly, you'll spend more time there than if you run across it, right? So increasing the flow rate will cause your average time spent there to go down. Now, what other quantity had that kind of property? I think about what among the variables we dealt with, there was something related to flow rate and volume, and right. So thanks, Vera. Right, tau, the space time. So space time, as we loosely explained, was gave us some measure of how long things were spending in the reactor, and now we have a precise way to evaluate it, right? And it's shown in the notes for different types of reactors. We can show that space-time tau is equal to the average age, and the average age is obtained in this way. So this is a very statistical way to get an average. If you take any distribution, even if in our class, if you take the distribution of height and you multiply by height here. So if you take the fraction of people having a certain height and you multiply by that height and you add up over all heights, then that's an estimate of the average height in the class. So in the same way, we've calculated the average age in the system. So this is a very statistical way to do this. Whereas with space-time, we wrote it like this, right? V over Q. We said the rate at which the volume is passing through the system divided by or on top or below the actual volume of the system, that must be the average time spent in the system. And if we think about this, these are the same thing, right? The average time spent in the space, the average time that it takes the fluid to cross the space, it's the same thing. So we can evaluate this in terms of the easily measurable quantities, or sometimes these are not known. Sometimes we are trying to get to the volume, but we know the space-time, then we can calculate the volume. So it gives us another way to get a handle on time. So all this is to say time and age are not really new concepts to us. They are part of the reaction engineering discussion that we've been having. And it's clearly important in the context of a reactor, right? The time that you've spent in that reactor does influence how much of that reaction will occur. So that's why it seems to be important to us. So the next question here, let's think about these different types of reactors. Let's compare what the RTDs will look like. So in this case, we have a plug flow reactor, right? And I know we said we are relaxing away from these ideal reactors. The whole point of this section is we don't want to only deal with perfectly mixed reactors, but still we can still work out what the age distribution will like for the ideal reactors. And in fact, we'll find that when we do that, it helps us to figure out how the non-ideal reactors behave. So let's take a step back and say, for the ideal reactors, how does the age distribution look? Right, so you've got a plug flow reactor. So maybe just take a second and sketch out for yourself what you think the age distribution should look like. Right, so I'll just pause for a half a minute and give you a chance to think about it, to just sketch out on a piece of paper what the age distribution should look like. Okay, so hopefully you've got something drawn out there, and let's think about a plug flow reactor. So you've got, here's your plug flow reactor. Here's a little plug for illustration. And let's think about doing that salt experiment where we blast up one of the plugs with some salt. Now, in the case of the plug flow reactor, all that salt is going to stay together. It's going to get into one of these plugs. So your salt is going to sit in one plug, and it's going to sit in that same plug as time goes on. That plug is obviously going to move down the reactor here, and it's all going to exit. So everything else will be exiting, and then the plug will exit all together as well. So what you will see at the exit point is, if this was time t0, and if t0 was here, and then if this is t1, then all that salt will exit at time t1 or tau1 there. So in the case of a plug flow reactor, your plug is all exiting at a certain time. And you'll see in the lectures that it's a Dirac delta function and so on. But for now, I'm just drawing it as a spike. So let's call this tau p. Now, and this is E, and this x-axis is theta, right? So that's all there. Now let's think about this case where there's some dead space in this reactor. So there's a certain dead volume. And, it could be anything, maybe there's some space here. So you've got a 50 cubic meter reactor, but in the corners, it's hard. There's a zero flow near the corners, so nothing. Or a bird flew into the reactor and it's consuming volume there, right? So for whatever reason, you've got a lower volume in the reactor now. So what's going to happen to your curve, right? When you didn't have dead volume, you have this spike. What happens to the spike when you lose volume in the reactor? So again, take a second and try and sketch out what happens in the reactor. Okay, so let's think about this. So if your volume is smaller, right? When we have dead volume, basically the volume is smaller. Then it's a smaller space to pass through. So let's say our volume now looks like this. So we have a smaller space to pass through. So we are going to pass through the space more quickly. In other words, our average age will go down. And so our curve would shift to the left here, right? So this is with dead volume. Okay, so that's one modification. And now let's think about a different case. What if we had some bypassing? What if our reactor was weirdly shaped like this? So let's say we had the reactor here, and let's say our feed point and our removal point was close together. And obviously this doesn't look like a plug flow reactor, but nobody said the plug flow reactor had to look like a long thin tube anyway. So let's say we had the case where there was some bypass, or never mind this weird case. Let's just say it was possible for some fluid to just bypass that reactor like that. What would happen to our curve in this case, right? So again, take a minute and just try and sketch out what would happen. Okay, so let's think about that. First off, if you put your pulse in here, that pulse is going to split. Part of that pulse is going to enter the reactor, and another part is going to go down here. And when we draw a bypass, we typically mean that it's a very fast flow. There's no volume to pass through, right? We regard lines as zero volume spaces. So this is just a pipeline, it's not a reactor. So there's zero volume here. So this part is going to appear immediately at the exit. So near zero, you'll see a first spike here. And then the rest of it will pass through the system here. Now, what's passing through will have a lower flow rate, because part of your flow rate has gone through this bypass line. So what's passing through here is passing through at a lower flow rate, but it's passing through the same volume, right? This case now doesn't have dead volume anymore. It's passing through the original reactor. So it's passing through, and it's going to take longer than the original case, right? This original case. So now it's going to pass through, it will take longer, and it will come out here. So this last case has two peaks, one near zero and one at a position greater than the original tau value. Okay, any questions or comments on that so far? Okay, so that's the plug flow reactor. Now let's think about the CSTR, right? So first, let's make a new space here. So in our CSTR, right, the usual thing, perfectly mixed, flow in, flow out. And now we're going to pulse some salt in here. And then how is that salt going to appear at the exit? So take a second and quickly sketch out what you think is going to happen to that pulse as it exits the reactor. So let's think about what happens, right? When the pulse enters here, it's instantaneously mixed, right? That's the feature of perfect mixing. So it's instantaneously mixing. So the concentration becomes the same everywhere in the reactor, right? Not the same as the plug flow reactor. That doesn't mix anywhere. It stays in the plug of fluid. Here it's instantaneously and perfectly mixed. So that means initially you have a certain concentration. and you are constantly withdrawing here, right? You are constantly removing material from the reactor. That's just because you have continuous flow out. So you are going to see some of your fluid exiting from that reactor. So if we were to draw it, we can say, well, if you've injected at time 0, then you will instantaneously, you will immediately see some salt exiting the reactor, right? So you'll immediately see some exiting here. Now, as salt is exiting the reactor, you are basically, so you are removing salt here, you are removing salt out here in this exit stream, and you are still feeding water. You are not feeding salt anymore, but you've got more water coming in. So you are in effect continuously diluting what's in the reactor, right? You are losing salt and you are gaining water all the time. So this is becoming more and more dilute, right? The salt is still in the system. It's still held up in this volume, but its concentration is going down. So what you'll get is a kind of serial dilution effect. And of course, as you get to the lower concentrations, the probability of salt reaching the exit goes lower and lower. And so your age distribution for perfect mixing is an exponential decay. And we prove identically, and not just intuitively, we prove identically in the notes or in the lectures, in the videos, in the other videos in the series, that it's an exponential decay. Right now, now the other questions: what if a bird flew into the reactor and you have dead volume? Right, think about what would happen to the age distribution and sketch on the same curve this case. Well, if you have a dead volume, then your space is smaller, so you're going to pass through more quickly. The same serial dilution effect will occur, and the same amount of salt has to pass through the system. So it's going to wash through the system more quickly, right? It's, less volume, so it's going to pass through more quickly. But to keep the same amount of salt, we can think of the area under the curve as being the amount of salt. So it's going to start higher and it's going to fall off faster. So you'll still get an exponential decay, which will start higher and drop off faster, right? So that's the effect of dead volume. Now think about bypass. What will happen in the bypass case? So here's some bypass. Okay, so hopefully you got somewhere with that. So in the case of bypass, you would find, number one, your pulse, some of your pulse will appear immediately at the exit, right? So you'll get a little spike coming through here. So you've got a spike coming through with the bypass. So if you like, that's a little PFR that's come through there, right? So we regard a bypass as a long thin tube like a PFR. So you've got a little spike coming through. Right now, even though these values start out not at 0, and I've drawn this one fairly sharp, but it's not a spike, right, by any means. This is just an exponential decay. But what's coming through here at time 0 is a pure spike. And then the rest of the stuff that does go through the reactor, that goes through the normal serial dilution and all of that. So, and now it's passing through more slowly. So this one is going to spend a longer time. The flow rate is lower, so it's going to spend more time in the reactor. So its drop off is going to be slower. So this one will, the second curve that comes through is going to start lower and last longer. Right, so that's what will happen in the bypass case for the CSTR. Then we can think about putting things in parallel. So like in this case here, you've got 2 plug flow reactors. Snoopy. Yeah, that was still test 1, not your test 2, in case you're wondering. So if you have your plugs in parallel, then you can imagine. So again, you can do the same thought experiment. You can pulse some tracer in here. And generally, if we've given different labels, we mean these are different space times. So the volumetric flow rates and the volumes are all different. So we can just call this tau 1 and tau 2. So we are going to get 2 spikes coming through. So you'll get one spike at tau 1 and another one at tau 2. Okay, so that's what you get in parallel. And then this case is quite interesting. So let's think about this. This one, maybe I'll give you slightly more time. So think about this case now and do the thought experiment, right? Imagine what's going to happen when you put a spike of tracer in here, right? In this case, you've got the plug flow reactor here. So VP1 is going through here. And then your exit point is here, but a certain fraction also recycles back. And this time it's not on a 0 volume line. There is a delay on this line also, right? We think of plug flow reactors as delays because it delays the whole thing by a certain amount of time. So there's another plug flow reactor down here, and the flow through that is opposite to the direction of the first plug flow. So see if you can figure out what this curve is going to look like. So any takers for that? Anyone like to talk about their thinking on this? I'm just going to label the space time on each of these so long. Maybe just to ask, does anyone think they have the right curve for this? Okay, so let's think about this. So we are spiking in some tracer here, and then it goes through the first reactor, right? For now, we can ignore what's coming in through here from the lower branch. So it passes through this first reactor. It's going to be delayed by tau 1. So we expect to see a spike appearing at the exit at tau 1. So that's there, tau 1. And then that's what we are seeing out here, right? So our measuring point is here. We can just forget about this thing here. Don't worry about the dead volume part. So we measure some stuff coming straight through the reactor. However, some of that salt will have passed down here. And here it will be delayed by a time of tau 2. So tau 1 plus tau 2 is here. And then it will enter here, and it will be delayed by a further tau 1. So here you've got tau 1, then this is tau 1 plus tau 2, and then this is tau 1 plus tau 2 plus tau 1. So this is 2 tau 1 plus tau 2, tau 1 plus tau 2. Okay, so you've got a little spike here. And this spike will be a bit lower than the first spike because what's coming down here, it's less than what, because it's split now, there's less coming through. And now when that plug enters here, when that plug reaches here, so the second peak we are seeing at this point. However, some of that has also split down here again. So you get another peak that comes through, which will also be delayed by tau2 and another tau1 before it appears here. So we get another peak here of 3 tau1 plus 2 tau2. And it keeps going like that. Each time you get another plug coming through, a fraction of it will get recycled. And so you have a series of disconnected peaks like this that never really die out. And the distance here is constant. The distance here is always tau1 plus tau2. And if you look at this curve, it looks like a combination of a CSTR and a PFR, right? You can see the height of these are going to be decaying because it's like a serial dilution effect. But at the same time, it's interrupted by this distance tau1 plus tau2. So it's kind of looking like a CSTR had a baby with the PFR, right? And the reason for that is you have a kind of circulation thing going on here. And at the same time, the actual delays in terms of discrete plugs here, right? So that's why you have this, that's why you see this, okay? So that's one of the interesting cases. And then you can also think about what happens with CSTRs in parallel and when you switch them around and all of that. Okay, so I'll leave you to play around with these ones also. Now let's think about this, this other interesting problem. So we are given some CSTR curves here, some RTD curves here. And we are told that we have this tube. So this is basically our reactor, and it's a multi-phase flow system. So we've got this tube. We have liquid entering at the top here. So it flows down through this bed. And then we have a gas bubbling up through here as well. So the flow rates are given. The space is packed with the solid particle material. And there may be a void space. Well, not really. Okay, so you've got, in fact, the total volume is known because you've got the cross-sectional area and you've got the height, right? So this is 20 cubic meters. You have these flow rates, and we want to know the fraction of the gas. So this volume here, what fraction is gas, what fraction is liquid? Oh, and there's a stagnant liquid. So there's a certain amount of liquid which is just sitting in this reactor, and that's taking up volume. And then there's a certain amount of gas passing through. So, and at steady state, there's a certain fraction of gas. So out of this 20 cubic meters, we want to know how much of it is gas at steady state, how much of it is flowing liquid, and how much of it is stagnant liquid. And if you think about it, it's quite a complicated problem, right? It's a very hydrodynamic problem, if you like. It heavily depends on the nature of the bubbles that are passing through, and how do those bubbles break up against this rock, and where is that stagnant liquid, and how much resistance does it give the flowing liquid, and then the fact that the air is pushing up here and the liquid is falling down there. It's all very complicated, and this problem would be quite impossible to do, right, without very detailed hydrodynamics. And so it looks like an extremely difficult problem to solve. I mean, it is a difficult problem to solve. And yet, and the measurements are not anything unusual. It's not like we've been given very special information here. We've been told, okay, the height is 20 meters, the cross-sectional area is 1 square meter, right? That's very easy. We expect to know those volumes. The liquid flow and the gas flow, we anticipate we can use the right meters to get those. So it's not like that's anything special. Voidage is possibly a little bit special, but that's not such a great thing either. So we haven't been given very special information, and yet we are being expected to figure out something that's quite difficult to get to. We don't see an easy way to figure out through all the hydrodynamics what the fractions of these phases would be. We do have some RTD curves here, right? And there, by now, hopefully, we don't think that's very special either, right? Because RTD is, we can see you just pulse some salt in, you measure a concentration with time, you divide by the area under the curve, and that's your RTD. So this also looks very simple to do. And yet we are claiming we are able to get these fractions. So maybe first, can you suggest how we can use this this information to get this to get these fractions? In fact, you need a bit of experience in hydrodynamics to know how hard this problem is to solve. Right, and now let's talk about how to solve it. Well, number one, for the liquid, you see this is a thin, it's a thin distribution. It looks like the average age here is 40. And maybe let's first talk about the fact that we have two RTDs here. We've got one for the gas and one for the liquid, right? And that might be surprising. You've been hearing about the RTD, and it's because you can have multiple RTDs. You can have in the Earth, right? If you may have noticed in the lectures, we talk about the Earth's age distribution. In the Earth, we can define for different countries, there are different age distributions. Each country will have a different age distribution. And you don't even have to have the population separated into different countries. You can talk about men and women. Men and women will have different age distributions. In fact, now you've got all those other genders also. You can't even keep track of how many there are. So you've got all these different age distributions. So different things can have different age distributions. So the gas may be spending a different time compared with the liquid. And it is spending a different time. You can see the liquid on average is spending 40 seconds and the gas is much less than 40 seconds. So your two different phases have two different RTDs. Now, in the case of the liquid, the average time spent is 40 seconds. And now you have the flow rate. And from this curve, what we can say is, well, if you are giving me the average age, if you are giving me theta over bar, you are in effect also giving me tau. And now with tau, I can stick in the volumetric flow rate, which is given. The volumetric flow rate of the liquid is known. So I can just work out the volume of that liquid. So it's as easy as that for the liquid, right? You multiply the volumetric flow rate by the space-time, which is nothing but theta over bar. And so that's the liquid volume already. We know the liquid steady volume in here. For the gas, it's slightly more interesting. We don't have the peak of this curve, but we don't really need it because for the age distribution for E, we are going to divide by the area under this curve anyway, right? So E is, where is E? Looks like we didn't write it here, but let's just write out E. So E equals C over integral of C. Right, so that's E of theta. And if we fix a constant, so let's just say we call the maximum point here K, then we can derive an equation for C. So these are just two straight line segments. So you get the straight line for this part. So you can just use K and 0 and 9 and 6, and you can get an equation there. And then you can get another equation here for between 9 and 15 and using K and 0. So two straight line segments. So you've got an equation for C here. And then the integral under that, you can just integrate the same function. You'll find the k's will cancel, and then you'll get an e. So you'll get an e function, and then you integrate under that, or you use this function, and then you can get an average age there. And you can see from this, it's probably about between 10 and 11. So it's somewhere here. So the average age, maybe it's about 10. Let's just call it a 10, right? So the average age for the gas is 10. And then you've got the volumetric flow rate here again. And so tau times Q equals V. So then you'll have the steady volume there. So you see already with the RTD, you are able to compute things that otherwise you have no hope of getting, not without very powerful computers and very sophisticated theory. You don't have to do as much hydrodynamics. With very simple measurements, you are able to estimate these difficult quantities. So that's part of the power of the age distribution. So that's how you solve that problem. Any questions or comments there? Okay, then moving on. So now we come to an interesting problem in terms of the reaction. So far it's just been about flow, and we weren't looking at any reaction. Now we have these non-coalescing droplets. So each droplet is its own identity. The reaction is happening inside each droplet. So we have dispersed non-coalescing droplets, all trying to say these droplets don't mix with each other. Each droplet starts out with 2 moles per liter of component A, and each droplet has this reaction going on inside. A is becoming R, right? The reaction rate is given. RA is, or minus RA is kCa squared, and the kinetic rate constant is given also. We want to know what the average concentration of A remains in the droplets as it leaves the contactor. Right, so let's just make our own sketch for this. Right, so we've got some reactor here. This reactor is of no known type, by the way. Right, that's why this problem is also interesting. That's also why this problem is interesting. If you look at this age distribution, this is not a thin peak. It's not a PFR. It's not an exponential decay. This is a curve that 0 here, it goes to some fixed number here and then goes back to 0. So this curve is, it doesn't match any reactor type that we are familiar with. And this could easily happen in reality. We can get some weird reactor, some weird mixing pattern that gives us this kind of age distribution. So this is some unknown reactor type. We have never derived an equation to be able to solve this reactor. And now we are going to claim that we can still do it, right? So first off, let's figure out the age distribution here. Now, we would like to take the trace, right, the C curve. We would like to take this and divide by the area under this curve. But if you look at this, we don't know what this value is, right? How are we supposed to get E of theta when we don't even know C of theta, right? Are there any suggestions? How can we get E of theta if we don't know the maximum value on this curve? The previous problem actually gives you a bit of a clue. Okay, we have someone. So Era says we could use the mass balance and find tau as V over Q. So yes, you can get a tau here. Just from looking at this curve, you can see the mean time here is 2, right? So you have 2. but then you need either V or Q and we don't seem to have that. V and Q are not given. Well, is the volume really not? Yeah, we don't have V or Q here, right? So yes, you can get the space time, but you can't use that to get. So you can get tau at least, right? We can say that much, but we don't know what to do with that tau in this problem. Now, one thing you could think about is if you look at this this equation, right? So Allegro Cube, sorry if I'm not sure how to pronounce your name, but divide C by K, so the unit will be in the. So yeah, you could define the maximum to be K, and then divide C by K. Well, I guess you are saying K is the area here. Okay, so that's a bit closer to it. Well, one of the things you could say is this curve, I don't know what the height there is. I don't know what that maximum value is, but I know E of theta is going to have the same shape, right? If you look at this equation, you've got C of theta here, and then even though you've got C of theta down here also, you are integrating over that whole function. So this is just a single number here. It's not another function. So basically the original function is directly proportional, or E of theta is directly proportional to C of theta. That means that your age distribution is also going to have the same shape, right? E of theta is going to be 0 up to 1. Then it's going to go up to some value here, and then it's going to come down to 3. So there's the 3. And now we do know something about E of theta. E of theta, the area under E of theta must be 1, right? So the integral from 0 to infinity of E. If you integrate over the whole function, it must be a 1. And the reason I'm saying that, obviously, if you follow in the notes, it's fully unpacked there in the lectures, I mean. But this is basically the fraction, right? In each sub-integral, if you are integrating E over a small range, it's telling you the fraction in a certain age range. Now here we are integrating over all possible ages. So this is basically saying all the fractions must add up to 1, right? In other words, the area under the curve E must be 1 always, right? So that area is 1. Now, if you look at this, you could define the height here to be K, let's say. So let's say this is K. And the area of this box then is the area under E. So the area here, so it's it's K. So the height K times the width here, which is 2, right? 3 minus 1 is 2. So that area is K divided by 2. 2 times K. So the area is 2 times K. And so that means K is a half. So your function E of theta, E equals, and I wonder if I can do those little curly things. Yeah, so E is 0 or theta is less than 1, so it's between 0 and 1. Then it's equal to K or theta being between 1 oops, between 1 and 3, and then it's 0 again. And we've just worked out that k is a half. So that's our E function. So we have, this is a half. Okay, so that's part of our problem solved. We now know how to get E of theta. Now, the other thing is, if you have followed the lectures, you'll also see that for the case where the reacting elements are completely segregated, then almost by definition, the segregation model applies, right? So if the reacting elements are fully segregated, then we've created a model called the segregation model. And the segregation model, using the segregation model, has this form. Right now, we've basically solved for part of this. We have E as a function of theta. We need X as a function of theta. So X is the conversion in the fluid elements. In the reacting fluid, X is the conversion. And in our case, we have non-coalescing oil droplets. That means we have little oil droplets here. And in each little oil droplet, the reaction is happening. So there's no reaction happening in the space between. So the reaction all happens here. So Ra is minus kCa, that's in the little oil droplet, minus, that's kCa squared. Now we can think of each oil droplet as its own batch reactor. So what we are really saying is we have this age distribution, and this age distribution tells us how each of these oil droplets are distributed in terms of the age. So it's saying at the exit point, there are no oil droplets which have spent less than one time unit in there. And there are no fluid elements that have spent more than 3 time units there. All of the fluid elements that come out have spent between 1 and 3 time units, and there is an equal amount of all those. So of all those that come out, you will have the same amount in 1 and 3, right? So it's a weird one, right? It's not a mixing pattern that we know or that we can easily justify, but that's what we can see in terms of what we've measured. That's what it seems to be, right? So we know what fraction of each of these fluid elements appearing at the exit, what fraction there is among the different ages there. But what we don't know is the conversion in there. Now, if we knew how long a particular fluid element spent there, so let's say we knew this one spent 1.5 time units in the reactor, couldn't we use this rate to figure out what the conversion was? Especially since we can think about each one as its own little batch reactor, right? Remember, it's staying as its own oil droplet. The reaction is happening inside of it. And if we are saying it's staying as its own little batch reactor, there's no flow into or out of this. It's an oil droplet, right? There's nothing that's coming into that oil droplet. So we can write a balance on each oil droplet as if it's a batch reactor. So we can say dCA T, and this is for the droplet, is equal to minus K times CA squared. And we can separate the variables, and we can rewrite this as dCA CA squared this is k dt here. And if you integrate this, it's going to give you 1 over CA. And that's between the initial value, so that's CA naught up to CA. Tech is letting me down here. Okay, let's do some. Okay, so yeah, we'll have to do it like this. I always try to avoid using this, picking through this menu. Okay, let's just type it, I guess. Okay. Get rid of this, right? And so that's the upper limit, okay? And then this integrated is going to be t minus t naught. Okay, so this is going to be 1 over CA minus 1 over CA naught equals that. And t minus t naught we normally think of as theta. So t naught is the entry time by the oil droplet into the reactor, and the current time is t. So the current time minus the entry time for that oil droplet, that must be the age of that oil droplet in the reactor. So we have this, and then we want CA. So we want to solve for CA here. So we're going to take this across to the right-hand side. So we'll rewrite this like this. So this is plus 1 over CA naught. And then we invert all of this. So we say CA equals 1 over all that. And then you can multiply top and bottom by CA naught. So you get your CA naught. This is 1, this is CA naught, okay? And it's maybe a bit better to write it as 1 plus this thing. Right now, what we, so this is giving us the concentration in an oil droplet of age theta, okay? Now, what we actually want is conversion. So if you want to stick with the form, you could change this form, but anyway, let's stick to this form and work out x of theta. So what we actually need is x of theta. So x theta equals 1 minus CA over CA naught equals 1 minus, and then CA over CA naught is equal to, you have to divide by this thing here, right? And then you've got 1 minus this. So you can bring that 1 into here. So it's going to be this thing, this whole denominator, minus 1. And you can see it's 1 minus 1. So you can just forget about the ones here. So that is your x your x of theta, okay? So that's what you do in the case of segregation, right? When your reaction is happening in different elements. So we now have each piece of this. We've got x of theta, we've just worked that out, and we've got e of theta. So we can say the solution we are looking for is this one, right? So we can substitute this thing in here. Now we can think about what's going to happen with this e of theta. So we've worked out that e of theta looks like this. Now we can see that e is going to make that product 0 here and 0 here. So it doesn't make sense to integrate all the way from 0 to infinity, right? For all values here, it's 0. For all values down here, it's 0. So we'll be multiplying by 0. So we will be going from 0 to infinity, but then integrating under 0. So that will add nothing to our final integral. So what we might as well do is say, look, it's going to be much easier to just go and integrate this from 1 to 3. Right, so first off, our limits are updated to a much smaller range. And then e of theta, we figured out in that range, it's only equal to a half, right? So that's nice and easy. And now you see you have a form which you can easily integrate. Right? You have the variable of the function is theta, and you've got the theta explicitly here. You've got the functions for this. CA0 is given in the problem and K is given in the problem. So you have everything that you need to evaluate this integral. And you can just pick a couple of values. So you can take at maybe at 0.5 and 2.5, and you can stick those numbers in here. And so you can just choose a couple of values inside and do a Riemann integral. So you can approximate this integral quite easily. Okay. Any questions or comments in that one? Okay, so that's question 4. And now we come to a kind of a full-scale Chem-Eng type problem using RTD. So this is, so all those shorter problems were illustrating the different points of RTD and how you can use it. So this is a kind of full-scale problem now where we are using RTD in the so-called compartment model. So in this problem, we are saying that we have a certain real reactor which is represented as a network of the ideal reactors. So this is a strategy towards modeling a real reactor. So like we said earlier, no real reactor behaves perfectly like one of those idealized cases, right? The CSTR and the PFR. We don't really talk about batch. Sorry, 1 second. Okay. So we don't really talk about those ideal reactors. We don't really talk about the batch case. The batch case we talk about in terms of individual oil droplets, but in terms of a real reactor that's flowing, it doesn't make sense to talk about batch so much. We usually talk about CSTRs and PFRs, and we create networks of those reactors to approximate the real reactor. So if you think about this case here, you might say, well, you could take a series of little peaks, or you might take a curve, which, well, okay, this one is not such a good example of that, but quite usually in your prac, you've got a curve like this. So in the practical you've done in this course, I'm not sure with COVID how much of this prac you've done, but in the practical, you are given a real reactor, a multi-tube reactor, and you have a water passing through it, and you pulse the salt in and you measure out a signal like this. And you can see that you can, in part of this curve, you can see CSTR-like behavior. In part of it, you can see plug flow-like behavior. So you get through a combination of the ideal cases, something that approximates the real case. And it must be said, the ideal cases are on opposite ends of the spectrum. So you've got the CSTR perfect mixing on one side, and you've got the PFR perfect not mixing on the other side. So the real world is somewhere between those two, between those extrema. And that's why it works. That's why it's often possible to represent a real reactor in terms of a combination of the ideal reactors. So you see, right from the beginning, when we started with those ideal reactor types, there was a reason for choosing those specific ideal types. It's because it turned out over time that combinations of those ideal types do give us reasonable approximations to these real reactors. So in this case, we find that we are trying to mix this real reactor, but what actually happens is, because of the viscosity of the fluid and maybe the nature of the material and how fast we are stirring, it turns out that all the stirring happens just close by the stirrer, and the rest of the fluid is flowing fairly regularly. Plus, it seems like there is a zone where the fluid just flows straight through. There's a region where the fluid seems to bypass the reactor. There's a region where the flow is not mixed that much, and there's a region where the fluid is mixed quite well. So if we think about this, we can imagine drawing this this real reactor, right? And all this is perfectly reasonable to us. This type of thing happens all the time, right? So we can think in terms of the ideal reactors. And maybe let's give you a minute to just sketch out the network of ideal reactors you would use to represent this real reactor case. Okay, would anyone like to share their thinking on how to draw this? So we've got, you can see a bypass here, but in the real world, this is not an infinite bypass. There is going to take some time to reach the exit. So let's draw that as a PFR. I wonder if I can't use one of these little shapes. Yeah. So let's say there's a little PFR here. And then we can see there's another PFR down here. And then there's a CSTR here. And if we think of it, there's one feed line. So part of that line will go straight through, part is coming down here. And we can think of these two as being in series. So we've got a line here. Okay, and now we're just back to sketching these things in. So my proposal here is that we have one long PFR up here, a CSTR down here in series with another PFR. right? So that's our proposal for a network that approximates this real case. And what we also have is this is an RTD measurement. We didn't actually read the problem. So CFD study was done. So when I say a CFD study, that typically means I'm justifying how we got this picture in the first place. So you can see little flow lines and things. So the velocity vector field, this is basically a velocity vector field that's sketched here. So if you do a CFD study, so that means you basically solve Navier-Stokes equations over the whole space to work out the local velocity vector field and the concentration and temperature. So if all that is done, you can get this velocity vector field. You are given the total volume of the reactor, and it's described that it seems like there's a bit of a bypass, and then there's a bit of mixing that happens near the stirrer. And then after the stirrer, there's something like a plug flow. So the text also helps you interpret this picture and think about how to create the network, right? So don't neglect the text that's useful also. We are also told the flow rate. So in the real world, that's the flow rate, right? So I'm saying in the real world because that's a measure, that's a real flow here. So there is a pipeline chugging along with that flow rate, right? And then inside the reactor, there are kind of virtual flows. So we can think of this split here as a virtual split. There's no real split. It's our concept of a split. There's a certain virtual volume. So there's a CSTR portion. And in the real world, there's no real boundary, but we'll think of an imaginary boundary. So there's a virtual boundary there. There are virtual boundaries for all these sections, right? So, but that's a real flow rate here at that inlet point. And then we can pulse tracer in this real flow, and we can measure a concentration here. And that's the RTD that's measured down there. Okay, now looking at this RTD, you can see a couple of features. So number one, we can see this spike here at 0. So that's telling us that this bypass is extremely fast. So it's approximately 0. So this is approximating an actual bypass here. So we could have just drawn this as a line instead of with a PFR there. Then there's some delay before we start seeing an exponential decay. So that's telling us that the delay that's given to us is from here. And now almost immediately we can write down some values. So the decay here is 2.5 seconds, right? So that delay means the space-time here is 2.5 seconds. Then we can see the exponential decay here. So that's clearly from this. And you might be wondering now, if we look at this, you can see the delay here and then the exponential decay. So why don't we draw the PFR first and then the CSTR second? And that's because if you pulse tracer in here, you will immediately get an exponential decay, but then that whole exponential decay will be delayed by this PFR. So you will still get 0. So the PFR, even though it's second, will still put its delay in front, and then the whole exponential decay will be delayed like that. So this, we can't actually figure out whether this should come first or that should come first. You'll get the same result. Your measurement will be the same. In fact, though, if we look at the picture, it does look like the CSTR should be first. So you'll still get the exponential decay coming out second, because the whole thing, the whole exponential decay will get delayed anyway. Okay, so that's the picture we have. And now we can use it to answer these questions. Any questions or comments so far on this? Okay, so let's go ahead and do this. Let's copy this picture first. And okay, we'll copy it with all the mess also. And now let's just do this on a new space. And the first thing that the question asks for is the network and then develop a model of the RTD. So what we can first do is define for ourselves the total volume of the reactor. So total volume and flow rate defined as V naught and Q naught respectively. And now we want to specify our splits. So we have a certain real, let's go back chart, right? We have a certain real flow rate here, Q naught. And what we are going to say is that a certain fraction of this flow rate splits off. So let's call that fraction beta. So beta Q naught goes up here. And then by definition, coming down here, 1 minus beta Q naught is what we have here. So 1 minus beta Q naught. We also have in total a total volume of the reactor V naught. And let's define the fraction that goes into this reactor as alpha V naught. And the fraction, the volume that's in this part, this will be 1 minus alpha V naught. We are not giving any volume to the upper part because we can see that spike appears immediately at 0. So that means this must be a 0 volume. So our real reactor is really partitioned into this mixed part and to this plug flow part. So let's copy, let's replace our figure with this version, which has the labels on it. Okay, now, so the flow rate, yeah, so to the CSTR part, so we can say tau S is the CSTR's space-time. That's equal to, it's going to be the volume, which is alpha times V divided by the volumetric flow rate, which is going to be one minus beta times Q naught. Right, so that's our space-time on the CSTR. Then the PFR, we can say tau P equals, and the volume here is 1 minus alpha times V naught. And all of this is divided by 1 minus beta Q naught. By the way, it's more efficient if I had chosen this to be beta and this to be 1 minus beta, because then we could have avoided, we won't be working that much on this upper branch because it's got a 0 space-time. So it would have been a bit better if I chose beta to be down here. But anyway, now we have one relationship already. We said that we can see the space-time here is 2.5. So we can write this down straight away. We can say this is 2.5 seconds. Right, so already we have two variables that we don't have values for, alpha and beta, right? V naught and Q naught are defined in the problem. So we have one relationship. Now we just need one other relationship. And to do that, we should look at the curve for any features that we can see. And one feature is simply the maximum point here. So we can think about, can we identify this point? Does that have a special value? And to do that, we actually need the model, which is what part A asked for anyway. It asked for the equation giving us this picture, or what's the model for this picture. So you'll see again in the lectures how to derive this fully, but I'm just going to write it out here. Theta is equal to, and in fact, okay, let's write it as Q naught times E. So the total flow rate of fluid elements between theta and theta plus delta theta is E theta d E theta d theta. Right, so that's the flow rate of that's the volumetric flow rate of a particular age, if you like. So that's what's coming out there, and then that's equal to the flow from the upper branch. So that's going to be beta times Q naught times, and this is the Dirac delta. So this is delta theta. Yeah. And this we should say d theta, right? And so that's the contribution at this point from the upper branch, and then we have to add from the lower branch as well. Now, coming from the lower branch, you have to look at your PFR in series with your CSTR, or CSTR in series with PFR. That's covered again in the lectures. So I'm going to write down the solution to that. It's basically 1 minus beta times Q naught d beta times, and then it's going to be 1 over tau s e to the theta minus tau p, and this is divided by tau s. Tau. Right, so please do work through this in the lectures, right? Understand about this plug flow in series with CSTR. So this is the equation for this is for beta greater than or equal to tau p. Now, if you look at what happens at tau p, or first, let's do some cancellations. We can see that the Q naught and the d theta can be eliminated. Or let me do this in a new Q naught and the d theta can be cancelled everywhere. And in fact, let's complete this equation also. You see, this is what you get for theta more than tau p. If theta is less than tau p, then you also have to add the iPad
back on charger. Daddy, put the tablet back on charger. Please put this thing back on charger. Please.
Sorry about that. So we are just trying to finish this equation because we said for when theta is more than tau p, then we have to, then we include this. We know that when theta is less than tau p, that we are still in delay. So this won't have appeared as yet. So for theta less than tau p, we won't have this exponential term contributing anything. So this will basically not appear. And we can see that in our in the graph. In fact, yeah, okay. I'll have to repeat doing the cancellations there. Yeah. Okay, so this is the complete model, right? This is showing for all values of theta, what E of theta will be. Okay, and now you can see in the curve, that's what you see as well. You don't get the exponential decay before that. You do get the spike, so the Dirac delta function, you get that, and then you don't see anything, and then you get the exponential decay. So when you switch over here, then you are adding that other term. But in terms of what we are trying to solve, so that answers part A. But in terms of what we are trying to solve for, we are looking for one other feature, right? Because we have one other unknown. So now we say, well, according to this equation, when theta equals tau p, I can see there's a special value that applies here. So let's do that. Let's apply tau p in this equation. So say now, we don't have to say for this, we are using that part. And when theta equals tau p, and we can say this is a tau p, so we can just stick tau p in where theta is. And then this is going to be tau p up here. So clearly that's a 0. So we are going to have x of 0, which is just a 1, right? So this whole thing becomes a 1. So it's like that. And this tau p also, the Dirac delta function is 0 everywhere at 0. Now tau p is not 0. So this is a 0, right? And again, look at the lectures, look at the Dirac delta function. Dirac delta function is 0 everywhere except at 0. Now, this is not at 0. Tau p is not 0, so this is not Dirac delta at 0. So this whole thing is a 0. So we can just get rid of that term. So now we are left with this. And if you look at the curve in the question, we have a value, we can take this as approximately 0.2. So this is 0.2. There is a little more work to do. This tau s, we need to use this here. So we can write 1 over this. So we should put this in the numerator. And so this is actually 1 minus beta squared. Okay, and that's the other relationship that we are looking for. So we have this relationship, and we've got from earlier this relationship. No, where's the other? This one. So 2 equations in 2 unknowns, and we can solve this now. And you see, again, we have taken something that's hydrodynamically quite complicated, right? This proposal of ours to separate our volume into these two virtual volumes and this flow into these two virtual flows, that's complicated, right? Think about what's happening here in the problem, right? In our original problem, we are talking about what is the split between what's flowing up here and what's flowing down there. And then what's the split between this mixed space and this real space? It's not at all easy to answer. In the real world, there's no defined boundary like this. But by simply pulsing in a little bit of salt and measuring a little signal out here, right, taking the signal, we are able to actually get numbers, right? After you solve the quadratic hidden here, after you solve this, you then actually have a value for beta and a value for alpha. And so you can convert this virtual model into something with defined numbers that tell you, if you were to model it this way, this is what those splits would be. So that's quite significant. It's very hard to do that with I mean, without RTD, you would have to do quite a lot of CFD and do quite a lot of hydrodynamics work. And now it's really simple. You only have to solve a quadratic here to get the answer. So now we have a practical way to take a complicated real world mixing situation and work out an equivalent idealized network. And we can use this network now to solve the other problems. And here you'll see there is a segregation type problem. Is this to say, yeah, solid particles reacting. So again, you've got particles that are flowing around this reactor. And so in this virtualized reactor, you've got particles flowing through. And again, you can work out a conversion and for each particle. So you can work out x of theta. And now we have a general equation for E of theta, and we have the alpha and beta. So we can get this function also. So we have both these functions right after you stick in the kinetics like we did in that earlier droplets example. So you can work out x of theta, we've worked out E of theta, and then you can work out the overall conversion in the segregation case, right? So we now have a way to solve even a complicated problem like this, even a case where there's imperfect mixing. We have a simple way to do it. We pulse in a bit of tracer, we measure the age distribution, and we can solve a sophisticated problem like this where the particles are spending a complex amount of time, right? Their distribution is complex. We can solve even a problem like this. So that's how you would go ahead and solve this problem, right? And in fact, this problem is something it uses some parts that occur later in this course. So you'll be seeing Prof. Lockhart soon. So he will take you through the solid particle interactions. But for now, you can just do the first part of this problem and use the segregation model. I would like to talk about just what if it wasn't about particles? What if there were not droplets or particles? Or so basically, if the fluid was not segregated, let's say this was just a continuous fluid like water passing through the system, and you had some component in that water, right, perfectly mixed with the water. How would you solve that problem, right? So in other words, we don't have this equation. We can't use this equation anymore if it's not segregated. If the molecules are mixed completely in the fluid and you still had this complicated mixing pattern. So non-segregation with complex mixing. How do you solve that problem? So any suggestions so far? So the answer is we've already solved problems like that, right? If you think about the first part of the course where you had, for example, CSTRs in series. So you had the CSTR in series, and when we did that, we were talking about homogeneous reactions. So reactions that were happening in the same liquid. We weren't talking about oil droplets or solid particles. We were just saying there's a reaction here, RA equals some function. So we were solving problems like this. So we could do the two CSTRs in series. Go away. So we've got the two CSTRs in series. Then we could also have done, I'm not sure how much we did of this, but you can easily say, okay, CSTR in series with the PFR. So we know how to write the design equation for a PFR and for a CSTR. In those cases, we knew the volumes and the flow rate. So we had the volumes of the reactors and the flow rate. And now through RTD, we do have those volumes and flow. We can get those volumes and flow rates. We can work out alpha and beta and estimate the volumes and the flow rates of all the pieces. And so we can just go ahead and use the earlier material balances that we had. Right, so that's how you would solve a problem if it's not segregated, if it's a homogeneous fluid. So everything is, if the molecules are mixed in the fluid and the reaction is happening in the fluid, then you just follow the same approach. You create the network of reactors and you work out the volumes and the flow splits. And then you just treat this as, okay, I solved the CSTR that tells me the concentration going into the PFR, I solve the PFR, get the conversion across there. It's the exact same thing that we did in the first part of the course. Okay, so the difference here is now we can do it on a real reactor. We just view the real reactor as compartments of ideal reactors. So this is an approach of compartmentalization, right? We've taken a real reactor and we've broken it down into compartments of ideal reactors. That's basically it. Any questions or comments there? So the test obviously covers all these sections. So the tutorial we had 2 weeks ago, which introduced the energy balance, and this tutorial, which introduced the unsteady state and the age distributions, all of this is on the test. Okay, then if that's it, yeah, you can I'll take any questions by email. If you want to have another session for further discussion, we'll do that. By the way, I will put out another pre-test, so please complete the pre-test like you did for the first test. You do the pre-test, and then you and it will follow the same format as the first test. So you answer those multiple choice questions through that interface, and there will be calculation questions and so on. So that's pretty much it. Okay, last chance for questions. Gone. Okay, that's it. Thanks, everyone. See you in the test then.